So write one question. One question you write. The mass of an electron. The mass of an electron is, what is the mass of the electron? Anyone? What is the mass of an electron? Anybody?
Ma'am, 9.1 into 10 raised to the power minus 31 kg.
Okay. The mass of this value you should by heart. The mass of an electron is 9.1 into 10 to the power minus 31 kg. 9.1 into 10 to the power minus 31 kg. If its kinetic energy is 3 into 10 to the power minus 25 joules J. 3 into 10 to the power minus 25 joules. Calculate its wavelength. Calculate its wavelength. Yesterday we calculated the wavelength of a ball. Now we are going to calculate the wavelength of an electron. Ball and electron. See the comparison? Ball and electron. Ball is very much bigger as compared to an electron. Yesterday we calculated the wavelength. If a ball moves, what is its wavelength? And we found out that it is 6.6 into 10 to the power minus 34 meter. The value 10 to the power minus 34, the value is very less. But now let's calculate the wavelength of this electron. For that, they have given kinetic energy. To find out the wavelength of electron, that means lambda. Lambda is equal to h by mv, h upon mv. H value we know, m value they have given. Velocity, that value we have to find out. Velocity value directly they haven't given. Instead, they have given kinetic energy. So half mv square is equal to this value. Half mv square is equal to this value. So from this you can calculate v, and that v you can substitute to find out lambda. So calculation is a tedious calculation, bigger calculation. First you find out v. So half mv square is equal to 3 into 10 to the power minus 25 joules. M you know, that is the mass of the electron. Mass of the electron, that is 9.1 into 10 to the power minus 31 into v square is equal to 3 into 10 to the power minus 25. So v square is equal to 3 into 10 to the power minus 25 divided by 9.1 into 10 to the power minus 31, and v is equal to under root this raised to the power 1 by 2. You have to find out the square root of this. Not easy to find out the square root of this. Still, you find out approximately. I am giving you the value, that is V is equal to okay, you directly calculate that. Directly we'll substitute that and we'll find the final value. Okay, V we have got. Now we are going to calculate the wavelength, that is lambda. Lambda is equal to h upon mv. This is the V. H upon mv, which is equal to h, that is 6.6 into 10 to the power minus 34 joules seconds upon m, that is 9.1 into 10 to the power minus 31 into this V, that is 3 into 10 to the power minus 25 into 2 divided by 9.1 into 10 to the power minus 31. This and the value, the final answer, I want to make you compare these answers. So this answer is coming as 8967 into 10 to the power minus 10 meter. Previously, in the case of ball, it was in the order of minus 34. Now this value, as compared to that value, this value is bigger. So wavelength of this electron is considerable. It will be 896 nanometer. 896.7 nanometer. That means this value is little bigger as compared to that ball. That means electron can act as a better wave than a ball. Why the ball is not able to act as that much wave? Why the ball cannot show that much wave property? Because of its mass. Its mass is very high. If mass is very less, then they can move as a wave. They can act as a wave. So electron, not a particle. It is not a particle. Instead, it is a wave. So that is the point we are learning from this dual behavior of matter. We have to come to this point that electron is acting as a wave, or electron has wave property. Right down. This shows that electron acts as a wave. This shows that electron acts as a wave. Electron acts as a wave. In the previous question, where you got that lambda for the ball, there you write in bracket very less value. In the previous question, where you found out lambda for the ball wala 6.6 into 10 to the power minus 34 meter. That wavelength is very small, 10 to the power minus 34. Here only 10 to the power minus, you tell me the value, 8.9 into 10 to the power 8.9 into 10 to the power, tell me.
Minus 12.
Minus
12.
8967 into 10 to the power minus 10 I gave you. 4 digits I have given. Right? So you multiply and divide by 1000. You multiply and divide by 1000, the value will not change. Right? So this 10 to the power minus 3000. So we have written like this 8.9. Now 10 to the power 3 and minus 10. So it will be 10 to the power minus 7.
Minus 7.
Okay. this is 10 to the power minus 7 and that one 10 to the power minus 34. So compared to that minus 34, this minus sign minus 7 is a bigger quantity. Minus 34 minus 7. So minus 7 is a bigger quantity. All right. So we are now reaching to this sentence. What is the sentence? Electron is acting as a wave. In the case of Bohr model, when Bohr put forward his model of atom, electron was a particle. Now De Broglie says that it is not a particle, instead it is a wave. So you have to consider electron as a wave inside an atom. How the wave moves? Like this, like this, like this. Wave moves. This is the wave character. This is the wave character. So Bohr was telling electron is moving round the nucleus in well-defined circular orbit. So you cannot say well-defined circular orbit, not circular orbit. Circular orbit hai to bhi, it is in the form of wave. So if this is the nucleus, this way, not the circular orbit, it shows wave character. Electron shows wave character. So you must have seen old 10 paisa, 10 paisa. Have you seen old 10 paisa coin? Have you seen? Not seen. You have seen only 2000 notes, right? Old 10 paisa coin. Those, please raise your hand. Those who have seen that. Please raise your hand. Those who have seen old 10 paisa coin. Okay, very few. Very few. Kangana has seen, Sahil has seen, Sujal ka video. Video kahan hai? All of you turn on your video. All of you turn on your video. Nishtal, Sujal, Somil, Ansh Yadav, Shivang, Pradisha, Sarav, Amisha, Rishi. Show your faces. We get energy seeing your faces. Our energy is your face. When we see you, we get energized. Okay, that is our force. Sarab, Sarabanam. Okay, good. Okay, so De Broglie is telling that forget about the circular path. Forget about the circular path, but it is an elliptical path. It is an elliptical path, wave motion. Electron is moving, electron is a wave, so it will show the characteristics of wave. It has got lambda, that is wavelength. Wavelength is a length, you know, wavelength is a length. Wavelength, last year you must have learned wavelength, crest to troughs. In physics, you must have learned about the wave. All right, there is a frequency for a wave, there is a wavelength. There is a wave means two things it has got. One is wavelength lambda and the other is frequency nu. So we are on towards quantum mechanical model. First aspect, we have proved that electron is a wave. Electron acts as a wave. It has got wave character, that means lambda and nu. So next concept is Heisenberg's uncertainty principle. HEI. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. The principle itself is an uncertainty, right? Heisenberg's uncertainty principle. It states that, means Heisenberg says that it is impossible to determine, write down first, it is impossible to determine, it is impossible to determine the exact position and the exact momentum, exact position and exact momentum of a microscopic particle, simultaneously and accurately. It is impossible to determine the exact position and exact momentum of a microscopic particle simultaneously and accurately. What does this mean? What does this mean? Position. Where is your position now? You are sitting in front of your camera, in front of your laptop or mobile. This is your position. And how much space you are occupying there? I can say this much size your body and this much your height, length. So this is your position, this much width. Okay, Sujal Sukeja of this much width and this much height. That is your position. I can locate you. I can locate you. Anshata, thoda sa little height, this much only the size. So this way we locate you. This is the size, length, breadth, and all. That is the position. You occupy this much space in this world. How much space you occupy, Ansh? This much space you occupy in the world, right? This much and this much. So that is the position. I can locate you. Can you locate an electron in an atom? Can you locate an electron in an atom? Okay, you use the electron microscope and look at this electron. This is the position. It takes this much electron. You can consider it as a small sphere. So this much width, this much height. Okay, this is the space. This is the position of that electron. To know the size of, for example, Ansh, I am going to measure Ansh's width. How much width, Ansh? Tell me your chest. You don't know. IPS नहीं जाना है. IPS police selection के लिए they show the chest and they measure that width. Chest width and the height and all, this much height is required, this much chest is required. Similarly, electron ka width, electron ka size, you can measure with its diameter, electron's diameter, or we said dimension. A height, weight, height and width, all we said dimension. We are going to measure the dimension of electron to know the exact position, how much space it occupies, how much space it occupies. For that, we want to know the size, its dimension, we call it as the dimension of the electron. What is written here? It is impossible to determine the exact position, means its dimension, exact position and exact momentum. Momentum means mass into velocity. Momentum sometimes, okay, we are taking it as velocity, mass is constant. So mass of the electron is constant, that means momentum goes for velocity. So you can talk in terms of this thing also. It is impossible to determine the exact position and exact velocity of a microscopic particle like electron simultaneously and accurately. Simultaneously and accurately. Two things you cannot measure. Heisenberg is telling that there is uncertainty. When it is uncertain, when you measure both together, when you measure both at the same time, there is uncertainty. If you are concentrating on position, then you cannot measure momentum. If you are concentrating on momentum, then you cannot measure exactly the position. So let's see. How do you measure the dimension of an electron? To check the position. To check the position is just like I told you, chest, height, uska size, how much space it occupies, what is the dimension of that electron, where it is located, what is the position of that electron, this position, it occupies this much space, that is what is meant by the location. So we are going to measure the dimension of the electron. To know the dimension of an electron, you have to measure it. You have to measure it. Measure. To know the dimension of an electron, we are going to measure it. To measure the dimension of an electron, you have to use a scale whose smallest division is smaller than the dimension of the electron. You haven't understood anything. Once again, I'm repeating the sentence. To know the dimension of an electron, to locate an electron, to know the position of the electron, to locate an electron, to know the dimension of an electron, you have to measure it. Its size, its dimension, you have to measure it. For that, to measure the dimension of the electron, you have to use a scale, length. You have to use a scale whose smallest division is smaller than the dimension of the electron. For example, this is a scale, right? The scale, 30 centimeter scale, 30 centimeter scale. Can I measure the width of this paper, thickness of this paper? Length, breadth, thickness. Okay. Thickness of this paper. This is a paper. This is a paper. Can you measure the thickness of this paper using the scale? Can you measure the thickness of this paper using the scale?
No, ma'am.
Parth Soni?
Yes. No, ma'am. We can't.
We can't. My question is, can you measure the dimension? Dimension, I am taking thickness here. Can I measure the thickness of this paper using the scale? No. So we should construct a scale whose smallest division is smaller than the thickness of this paper. Am I right?
Yes, ma'am.
Yes. I should construct a scale whose smallest division, here the smallest division is, how much smallest division? Tell me. That's
0.1 centimeter.
Huh? Is it 1 centimeter?
1 centimeter. 0.2.
0.1 centimeter. 0.1 centimeter. That means 1 millimeter, isn't it? That smallest division is सबसे छोटा सा. Even that division is bigger than the thickness of this paper. I think almost 7-8 papers together I can fit into that. Right? So, to measure the thickness of this paper, dimension of this paper, I should construct a scale whose smallest division is smaller than the thickness of this paper. Right? Similarly, to measure the dimension of the electron, I should use a wavelength, a wavelength whose smallest division is smaller than the dimension of the electron. Then only I can measure the electron. Right? Okay. Suppose I have made such a wavelength. Suppose I have constructed such a scale whose smallest division is smaller than the dimension of the electron. To see the electron, I have to illuminate that electron. I am using a light. Light is a wave. It has got wavelength. So I should select a light whose smallest division is smaller than the dimension of the electron. Means I should use a light which has got wavelength which is having a lesser wavelength than the dimension of the electron. So lambda of the light used to illuminate that electron should be very, very less. Lambda of the light is away. To see that electron, I have to illuminate that. Means I am using a light. The light has got a wavelength. That wavelength should be very small, smaller than the dimension of the electron. So lambda should be very small. Lambda, we know the lambda is equal to h upon mv, yeah, h upon p, or p is equal to h by lambda. I'm using, can you see the board? Can you see the
Yes,
board?
ma'am.
Okay.
Yes, ma'am.
Okay, so I'm using a light of very, very less lambda. I'm using these photons of very, light means photon. Light is made up of photons. Light consists of lot of particles called photons. Photo, light, PHOTO. So I'm using a light whose wavelength is smaller, very, very, very small, smaller than the dimension of the electron. You know dimension of the electron. So I'm using the light, or I'm using the photon whose wavelength is very small. So what about its momentum? What about the momentum of those photons? Very high momentum. Means I'm throwing photons to see that electron. I'm throwing those photons. So these photons are going and hitting that electron, and that electron's momentum or electron's velocity is going high. What I wanted to locate I wanted to know the position of the electron. I wanted to know the position of the electron. अभी क्या हो गया? उसका velocity change हो गया. Electron का velocity ज़्यादा हो गया. Electron velocity, it started moving with high velocity. So if you are concentrating to know the location, or if you are concentrating to know the position of the electron, what happens? Its velocity is increasing. I wanted to check the position of the electron. For that, I was illuminating that electron with the photons of very low wavelength. But such photons are having very high momentum according to this equation. High momentum photons are hitting on this electron, and this Bechara electron started moving with high speed, with high velocity. That time when I was measuring what was the velocity, now that is not the velocity. The velocity is increased high. So at that particular moment, I was concentrating to know the position, but the velocity is now changed. Now the momentum is changed. Mass is the same. Now the momentum is changed. So that's why, so Heisenberg is telling that it is impossible to determine the exact position and exact velocity of an electron simultaneously and accurately. If you are concentrating on the position, the velocity will be changing. If you are concentrating on velocity, the position will be changing. So he says that it is impossible to determine the exact position and velocity of an electron, of a microscopic particle. To know the path of an electron, we should know both of this. To know the path of a car, C-A-R, the trajectory of a car, the path of a car, we should know its exact position and exact velocity at each and every point. Suppose there is a car. A car is moving. What is the path of the car? What is the trajectory? What is the trajectory of the car? To know the trajectory, whether car is moving in this way or car is moving in this way. To know the path of the car, to know the trajectory of the car, we should know its current position and current velocity. In the case of macroscopic particle, bigger particle, it is possible, but in the case of microscopic particle, it is not possible. So, since it is uncertain in its position and velocity simultaneously and accurately, how can you talk about the path? How can Bohr talk about that electron is moving in a circular orbit? Heisenberg is telling it is wrong. You cannot predict the path of the electron. So Heisenberg is telling you can say the probability of finding the electron, not the exact path. So now we are putting a new term, orbital, which shows the region around the nucleus where the probability of finding electron is maximum. Maximum. The region around the nucleus where the probability of finding electron is maximum, that is called as orbital. So with these two aspects, we are cutting that circular path and we are telling, हाँ here इधर देख सकते हैं, वहां देख सकते हैं, यहाँ देख सकते हैं, like this, like this, like this, like this. It is only a probability. Okay, thank you. I'm stopping. Don't leave. Don't
Thank
leave.
you.
Don't leave. Okay, thank you.
Thank you, ma'am.